Yeah, thank you. So today I'm going to talk about making large language model inference go fast. And ideally, we would ask, NVIDIA or AMD to make a GPU printer for us. Unfortunately, they won't do that because I guess that's their business model, selling GPUs. So we have to do other stuff to make it fast, right? So in this talk, I will first show you a bit how you can deploy your own models, and then I will show some techniques to make it faster. Well, I already had an introduction. So I work at Hugging Face on inference. So one term you will see a couple of times in this presentation is TGI, text generation inference. And this is an inference engine that I work on with some colleagues. There are some other inference engines as well, which I will mention later. And yeah, I'm a fan of a lot of tech stuff like NixOS or Rust, and I guess there are more Rust fans here, I hope. Okay, so I guess the main motivation for this talk, or one of the main motivations, is the trajectory of that large language models are taking. So this is a graphic from Maxime Le Bon that he posted a while ago on X. And I kind of like to think about back to the previous Pygrunn. And so we were here, right? And everyone last year, well, not everyone, but most people were talking about GPT-4. And there was a very good reason for that. And that was that GPT-4 was so much better than the competition that, it didn't make much sense. Well, it made sense, but like it did make a lot of sense to use GPT-4. However, now we're a year later and things have changed drastically. So as you can see, like the green dots here are open weight models. They are models that you can download freely, you can use, and you don't need to consume some API from a proprietary provider. An interesting thing you see there, and remember this is already about 2 or 3 months old, and the score is even higher now, but we can see that the gap between open weight models and closed models is narrowing, right? So we're almost at the point where a model that you can download freely does as well as one of those closed models. And in some cases, if you have like specialized models that are fine-tuned, they even do better than something like GPT-4o or one of the other proprietary models. And I think this is really exciting for us AI builders because it means that we can take control back. We can decide on our own destiny. Well, that sounds maybe a bit dramatic, but you can imagine that it's really cool, right? Because you can run an assistant on your local laptop using, for example, llama.c++. And no data leaves your laptop, your privacy is guaranteed, so that's really cool. Or if you're working in a company and you're deploying LLMs, you can just deploy them on your own servers, right? Because you have the models. Or if that seems to be too much work or too expensive, you can go to one of the inference providers and have them host the models for you. And you have the freedom to choose the inference provider. Maybe one is faster or maybe one is cheaper. You can go wherever you want. But I think even more exciting is the other stuff, which is like the power of having open weights. So first of all, you can inspect the model, which is kind of cool, right? If you're hosting the model yourself, that your data isn't going somewhere and they're using it for their own purposes. But you can also fine-tune models for your particular applications. And this doesn't have to be that resource intensive if you use one of the new algorithms like QLoRa. You can also, if you use such a model and you think, well, it's too big and too slow for me, you can compress the model to make it faster and more lean. And finally, and this is really exciting, you can remix the models, make new versions of it, and share it with the community. Or the other way around, you could look, say, on Hugging Face Hub, and there are millions of models there, and you could see if there is a model that is useful to you and download it there. So I think this is really exciting because, yeah, we can make our own models, we can deploy them ourselves, and that's pretty cool, I think. All right, so we'll slowly move towards inference. And before understanding how to make inference go fast, we have to know a bit about GPU architecture because it helps to understand why a model can be fast or slow, besides the obvious reason like it's big or something like that. And if you look at a GPU, so this is sort of the layout shared by most GPUs, what you see is that a GPU has streaming multiprocessors. These are the SMs here. And I only drew 4 here, but in reality there are tens or hundreds. And each streaming multiprocessor in itself has many cores, so these green thingies here. Besides that, each streaming multiprocessor has some control logic, and it has a small amount of memory. And this memory is extremely fast. So it's actually kind of hard to get these numbers from the specs, but it turns out that something like an NVIDIA L4, which is popular for inference, can transfer 22 terabytes per second from this tiny memory to the cores to do the work, right? So that's pretty fast. However, it's only 120 KB RAM. Well, I guess it's not true, but Bill Gates said something like 640K is enough for everyone, but obviously it's not going to be big enough to run an LLM. So we cannot stash all of our layers in these small memories. So for that reason, we have global memory, and this is much bigger, like on an L4 or an, I guess, a 4090. This is about 24 gigabytes of RAM. However, you already see the downside, right? It's almost 2 orders of magnitude slower than this very small memory in the SMs. So why do we care? Well, our models have a lot of parameters, right? And they live here in global memory, down here. And in order to do any computation on them, we have to transfer pieces to that small memory. And in terms of computation in a GPU, that takes ages. Well, these cores are extremely fast. All right, so that brings us to the roofline model, which is kind of nice to understand how well algorithms work on a GPU. So if you look at the specifications of a GPU, you will often see like this GPU can do that number of teraflops. And teraflops means floating point operations per second. So it's like adding a number or multiplying a number. That's one floating point operation. And you think, well, cool, I bought this new GPU and I'm going to use it in my company. And then it turns out that you don't reach that number of flops. Why is that the case? Well, it turns out that this memory transfer is the big problem, right? So what happens, for example, if you would write a very simple algorithm that just multiplies every number in an array by some scalar value, right? So that's just one floating point operation. What will happen is that these many cores can compute this insanely fast. So the cores will do their computation, and then they will be like, Jan, I'm going to wait until the next part of the array comes from memory, right? So in this case, you're in what we call a memory-bound regime. So the algorithm is mostly waiting for the data to come from the GPU's global memory, and it's not doing many computations. So what we can do is make more algorithms do more work. And if we do enough work, then we end up in the compute-bound regime, where we're not mostly waiting on stuff to come from memory, but we're actually mostly doing computations. And that way we can reach the peak number of flops. So in a lot of cases, what you want is you want to get at some, say, the boundary between memory-bound and compute-bound. Because in a lot of cases, it's actually quite hard to get to compute-bound. Okay, that's the theory mostly. So now we go to do some practical stuff. So we're going to set a baseline and see, if you're deploying an LLM, how is it doing? How well is it doing? Is it fast enough? Can it handle the number of users that I have, etc. And we're going to do this by loading up a model. And we do this using TGI. Could use VLLM or SGLang as well. There's different inference runtimes. And I'm just starting it here with text generation launcher. If you use a Docker image, you would replace this by Docker run, and then it works. And you give it the name of the model you want to load, and this model gets loaded from the Hugging Face hub. So what happens is the model gets downloaded into your local cache. From there on, it's not downloaded anymore, but always loaded from the cache. And then finally, we give it a port. And then when it starts listening on this port, and then it exposes an HTTP API. And this API, you could either use the TGI API or the OpenAI API. So it's a drop-in replacement for, say, OpenAI. Okay, so then we want to know, okay, how fast is this model on our hardware? And TGI includes a nice tool called Text Generation Benchmark. And you can use it to benchmark the deployed model. The only thing we have to do is we have to give it a name of a tokenizer. And the reason is that it likes to send text for the benchmark to the server. And it needs to know how many tokens am I sending. OK, so when you do that, you get this graph. So there's a lot going on here. So I'll explain, try to explain it a bit. So first, this graph, or the whole screen, is separated into 2 parts. The left part and the right part. And they may need different things. So the left part is what we call prefill. So prefill is basically the tokens you give as a user when you're giving a prompt to the LLM, right? So you give it like your whole 1,000 token prompt, and that part of the processing we call prefill. So once the prefill is processed, so that happens all at the same time, the LLM starts generating, because as most of you probably know, an LLM generates tokens one at a time, right? So this is what is described on the right-hand side. That's the decoding. So this is the stage where we return tokens over and over again until we reach some stopping token or whatever reason it could be to stop generating. Then there's this division between the upper side and the lower side. So the upper side is about a specific batch size. So I guess you could see up here, oh, my remote seems to bill out. Oh, here it is. There are some tabs here. You can switch between these tabs and look at different batch sizes. And then these statistics update for the batch size you've selected. Well, what is a batch size? Well, batch size 32, the size I'm currently looking at, basically means the performance if I had 32 concurrent users. Okay, so when I have 32 users, this is the performance, and I could also, switch to one user, which is probably not that interesting, but compare the statistics. Now then for prefill and decoding, we see some statistics. This is the latency, so that means this is the time the user has to wait until the user sees the first token being generated. So it's the time that we process the prompt. Of course, this is very much dependent on the length of the input you're giving. Then below that, we have the throughput. So that's the number of tokens per second we're processing with 32 concurrent users. And we see similar statistics on the right-hand side for the decoding. So this is the decode time, including the average decode time, which is about 38 tokens. This means that a user sees like 38 milliseconds between each token as it's generated. And finally, also here, we see throughput. So the throughput of decoding is actually much lower than the throughput for prefill. Can somebody shout in one word, or two words, why that could be? Otherwise, I'm going to give the solution. It's memory bound, right? So we're only generating one token at a time. Okay, for 32 users, but we're still only generating one token at a time. That means we have to retrieve all the model parameters for this one token, right, for generating it. And in the case of prefill, we're processing, say, 1,000 tokens at a time, and we still have to load all the layers of the model, but we do a lot of work, right, on all these 1,000 tokens times 32 users. So there we are compute bound. Okay. Oh, sorry, I forgot the lower part. So the lower part is not for a specific number of concurrent users, but for all of them, right? So this red dot here would be one user, and like the white one up there would be 128 concurrent users. And it displays the latency against the throughput. So like the lower side here, we have the latencies, and here we have the throughput. So what does that mean? Well, what you want to look out for is basically a vertical line. Vertical line is good because it means that as we're adding users, we get more throughput, but the latency doesn't get higher, right? The user doesn't have to wait longer. So here we see like at some point, it starts to flatten out. And the same is the case here. Like here we're doing well for certain throughput, but at some point, like if we have 128 concurrent users, then the latency really starts to suffer. And it means that every user has to wait longer for their token. So what do we do in that case? Well, either we do one of the optimizations we see in a bit, or we buy more GPUs and machines, right? So that is the point that you know, okay, we should scale up. So when you quit this utility, you get another nice table. It's actually markdown, so you can paste it in Obsidian or whatever. And this gives an overview of all the statistics for all the different numbers of concurrent users, right? So it shows the latency on the upper side and the throughput on the lower side. I usually really like this because you can make nice graphs out of it. Okay, so that brings us to the first optimization, and it's a very simple one, but works very well in practice, which is to introduce parallelism. So like when I just did the benchmark, I did it on one GPU. And that means that like a neural network, like an LLM, is composed of many layers, right? The data flows through all the layers, and in the end, it predicts a token. And if you only use one GPU, all those layers are stored on one GPU and processed by one GPU. So what we could do is we could introduce parallelism, and there's several types, but today I'll only talk about tensor parallelism. And what you do in tensor parallelism is you split up each layer in two, for example, if you have two GPUs, and then store one part of the layer on the first GPU and the other part on the second GPU. And you also do the processing like that, right? So one GPU is going to do the first half of the layer, the other GPU is going to do the second part of the layer. Well, I think you probably think, well, something is fishy going on here, right? Because how can it be? Because now they have different separate outputs. Can that work? Well, it turns out it works, but that's also a bit of a downside. Between the layers, you have to do some synchronization between the GPUs so that the results of both GPUs are combined. So for this reason, theoretically, it can make the throughput twice as fast. In practice, it's going to be a bit less than that because of the synchronization. An alternative is like you could say, okay, I don't care about the model going faster, but I want to load a model that is larger than my current GPU. And then you could use two GPUs to spread out the parameters across them. So how do we do this? So for example, in TGI and in the other inference, it's pretty similar. You just add a flag to your starting prompt, or not prompt, a command. And you say, OK, I want 4 GPUs. This is called number of shards in TGI. And so we want to see some benchmarks, right? So this is the results. On the y-axis, we see the number of tokens per second. And here we see the batch size, so the number of concurrent users. And the results are shown for 1 GPU in blue, 2 GPUs in green, and 4 GPUs in pink. And you might wonder why 1 to 4? Why are we not looking at 3 GPUs? Well, the thing is, if you're splitting up models across GPUs, it should be splittable, right? And it tends to be the case that people make models, make the number of parameters powers of 2. So you can nicely divide it. So dividing by 3 is not going to work unless you do padding and stuff, which is icky. So, right. So as you can see, it works pretty well. Again, you don't have 2 times scaling, but using 2 GPUs is definitely much faster, right, than using 1 GPU. And the same is true for 4 GPUs. OK, so the other benefit that I mentioned is that we can load larger models. So, for example, if we take a model like Llama 3.1 with 8 billion parameters, an open weight model, we can run it on 1, 2, or 4 GPUs. It's a small model, it works. However, if we try to load something larger like Qwen 2.5 with 14 billion parameters, well, it doesn't work on 1 GPU anymore. It's too big, right? The number of parameters times 2 is usually the size of the model in bytes, so it doesn't fit in a 24 gigabyte GPU anymore. But if we use 2 GPUs, we can suddenly load the model. And a similar story applies to even larger models. Well, you could say, why don't I just buy a larger GPU? Well, I'm not sure if you looked at the prices of GPUs, but like an H100 is like obscenely expensive, right? And sometimes you can get away with just buying 4 cheaper GPUs and have about the same amount of memory, and then you can use larger models at a much lower cost. All right, so let's go to the next optimization. So remember that I said decoding is memory bound, right? So couldn't we just try to move less data to the memory all the time? Well, it's an interesting idea, especially if you consider how large these models are, right? So something like Llama 70 billion is 140 gigabytes of memory. And even each layer is extremely large. So it makes sense to try to make the amount of data you load smaller, right? And one way of doing it is to say, oh, we're just going to halve the number of parameters in some way. So one way you could do this is by using quantization. So suppose that you have something like Llama, which uses 16-bit floating point numbers. This is like the default nowadays. Like in the days of BERT, the standard was 32-bit floating point, but we discovered like, OK, 16-bit works as well. So all the models are float 16 or bfloat 16 nowadays. And you're going to say, well, OK, I want to transfer less data between the layers. So what I'm going to do is like I'm going to switch from a 16-bit data type to an 8-bit data type. And twice smaller, so it's going to be twice as fast, right? So that's pretty cool. Well, that's true, but you're also throwing something away, right? When you go from 16 bits to 8 bits. Right, so you can see, for example, that the scale of bfloat 16, like the minimum and maximum value is insanely big, whereas for float 8, it's only minus 448 to 448, right? So there are going to be parameters that are not going to fit into that smaller type. So what do we do instead? Well, we just scale everything so that it does fit in a float 8, and then we're fine. All right, so what if we wanted to deploy a model like this? Well, we have several options. First of all, something like TGI has a quantizer implemented in TGI itself, and you can ask it to quantize, to make the parameters smaller while loading the model. So this is pretty simple. You add a flag where you say, okay, please quantize it for me to FP8, and then it does it while loading the model. The other thing you can do is you can get a pre-quantized model. For example, NeuroMagic has a lot of models on the Hugging Face hub that are FP8 quantized, and you could just load up that model, and the inference engine will see, oh, hey, this is an 8-bit model, so I'm going to load it like that. You could even go smaller, like there are also 4-bit models using int4. Of course, something is going to give at some point, because 4 bits, that's 16 different possible values, right? So there will be a loss of accuracy when you do that. So once you start quantizing in these extremes, do an evaluation. Don't make your users upset, do an evaluation. And then, if you conclude it's acceptable, do it. All right, so what performance improvements did we get from this? Well, it's even a bit more spectacular, I guess, than multiple GPUs. So here I'm benchmarking just on one GPU. And the blue line is like the original model. And the green and the pink line are 8-bit models, so float 8 and int 8. And finally, the yellow line is int 4. So it's a lot faster than FP16. And this is mostly due to the memory transfer, because I benchmarked this on a GPU where we actually don't use the native FP8 support of the GPU for reasons. So the other cool part is that besides being faster, you could also say, okay, I don't want it to be faster. I just want to load bigger models because they're more accurate. And well, you remember the previous smileys and cries. And you see now that we can load Qwen 2.5 even on one GPU, and the very large 32 billion model we can load with 2 GPUs, whereas we couldn't do that before. Okay, so one final optimization. This one is more difficult. I hope that I can manage in time. Okay, so in an inference engine, we need to keep track of stuff we did before, right? Like if we had a prefill and we generated 10 tokens, when we're generating the next token, we still have to look back at all the tokens that came before it, right? Otherwise, the model wouldn't know anything about context. So what we do in the inference engine internally is we keep some representation of all the tokens that we've seen, which takes up memory. However, we don't store it contiguously in memory. We don't store this 1,000 token sequence. The representations of that is just one long array. What we do instead is we do something like virtual memory management as in an operating system. So if you have some sequence like the highest mountain of the world is Mount Everest, so Mount Everest are now the generated tokens, even though logically you can think of these tokens to be consecutive, in memory, they're actually scattered across different blocks, right? So you see that the initial part is in the first block, and then we have some stuff down there. And so it's scattered through memory. But we can always reproduce the original sequence by keeping track of these pointers, the first logical block is the first physical block. The second logical block is the fifth physical block, etc. So it's kind of cool because in this way, we can dynamically allocate memory. We're not wasting space. We're not introducing a lot of fragmentation. This works pretty well. However, until recently, we had one sin, which is if we're done with a sequence like this, we free the blocks so that they're available again for other queries. But that seems kind of a waste, right? Because suppose that now the user says, the user is very interested in mountains, and now says the highest mountain of continental Europe is. And we just threw away the representations for the highest mountain of. So now we're recomputing it again, which seems like a bit of a waste, right? So to solve this, we use something called prefix caching. And the idea is to hold on to the blocks as long as possible and only deallocate them when we really need the memory. And to do this, we introduce another data structure called an affix trie. And the affix trie stores things as prefixes. So you can see on the edges here, you have parts of prefixes, and the nodes are the blocks where the prefixes are stored. So suppose that you do a new query, and the query is something like, you are a friendly assistant giving short answers about the beautiful city, Groningen. How you could then work is you go start at the root, and you check, well, is the first part of my prompt in there? And you see, oh, I have you are friendly, so I can reuse block 8. And then I also have, starting from block 8, assistant giving short answers, and take block 11. So block 8 and 11, we don't have to recompute, and we only have to recompute the part about giving answers about Groningen or whatever. Right? So in that way, we can reuse work that we have already done before. So what if we actually do need memory? Well, this data structure helps as well, because we don't want to start deallocating random stuff, but we can start at the leaves, and we just deallocate the leaf that is the least recently used, because that prefix seems to be the least interesting, right? And in that way, we free memory. Now, the cool thing is that for nearly all models, at least in TGI, this is automatically used now. There are some exceptions for reasons, but the vast majority of models use it. And while starting TGI, you can see, like, if it says use prefix caching is true, it uses that. Okay, I wanted to show a nice graph here as well, but this is actually pretty difficult to benchmark because it depends on the usage patterns, right? Like, if every user sends a vastly different query, then no caching, well, the caching is not going to do any good, right? Whereas if you would always send the same query, it would be nearly instantly done with the prefill. So a colleague of mine did some benchmarking by using the mixture of experts model and a data set of about 500 to 1,000 tokens, and then tried without and with prefix caching. And you see that like the time for the prefills is reduced substantially. And this is good, right? Because that means the user is waiting less long for the first token to arrive. Well, if I had 2 hours, I could go on and on about optimizations, but unfortunately, we don't have that time. So yeah, start building AI models on huggingface.co. You can upload your own data and models. You can download data models there. If you want to try text generation inference, it's an open source project. You can clone it and run it locally or run it through Docker. And yeah, that's it. Thank you.
Very cool, very cool.